Thanks, Matt.
There we go. It worked. It's all yours, Matt.
Okay, well, thank you. We appreciate being invited to talk today. This was a very cool project, not a project you get to do every day, and it's always nice to share those experiences with everybody. One question I was asked when I was asked to do this was why on a forum that's focusing on watersheds and more green infrastructure type activities, traditional pipeline is being requested to be talked about. I think the answer to that is the sanitary sewer systems on these communities that are along the lakeshore are critical to maintaining a healthy environment. And this project focused primarily on a densely populated area on the Grand River with high water tables where infrastructure for sanitary sewer is critical. And here in this case, it was aging and needed to get replaced. So as the description described, this project entails we were working for the Grand Haven Spring Lake Sewer Authority, and the Grand Haven Spring Lake Sewer Authority treats the wastewater for the cities of Grand Haven and Ferrisburg, Village of Spring Lake, Grand Haven Township, and Spring Lake Township. City of Ferrisburg, Spring Lake Village, and the township are both located on the north side of the Grand River, and the treatment plant is located in Grand Haven on the south side. Clearly, there's an issue there with a river between the two. So the Ferrisburg, Spring Lake, and the township, all their wastewater is currently collected into a central lift station, which on this map is shown on the north river's edge in the village of Spring Lake. This sanitary pump station pumps it across the river and where it ultimately discharges into the wastewater treatment plant located along the south side of the Grand River here. It's actually adjacent to an RV park. So if you like camping and you like wastewater, it's an ideal spot to go. This Forcemain was constructed in the 70s. It was constructed using river crossing, ductile iron, bell and spigot pipe, utilized the open cut trench method by barge. It was installed with only between 5 and 10 feet of cover between the top of the pipe and the river bottom. And it was placed in soils that consist really of primarily organic silts. And it functioned great. It was a 12-inch Forcemain. It functioned great for years. We had 2 issues with it. 1970s was installed, like I said, and in 1998, the pipe was broke. It was believed to have been caused by a barge strike, which is very possible to happen in this case when it was only 5 to 10 foot depth. That was repaired, and then in 2017, again in February, the pipe failed again. This time it was believed to be external pipe corrosion due to soils. In both cases, it was repaired using a band clamp as seen in the picture there, using divers to fix it. Both did result in raw water spill into the environment. With the second one, Eagle did get involved somewhat, and it was placed as a high priority from the authority to replace this line. So Prina Newhoff was retained by them to analyze the pipeline and how best to replace it, and then design the solution. So we knew we had to fix it. It was old, was starting to corrode. So the big question is, how do we fix it? This location was about 3,900 feet long, open water. And to install it with the method that it was done before, which was the open trench method, would have been quite extensive project. Back then, a 5 to 10 foot of cover was okay. That was not okay anymore. Now the Corps of Engineers would have required us to do about 15 feet of cover on the lake bottom or the river bottom. In order to dig that deep in the soils that were there and the amount of flow coming down the river, that would have required tight sheeting the entire crossing. The picture here on the left is example of this type of a crossing. Now, this is a much shorter crossing than what we were going to propose. And you would not have had an excavator on top, but it would have been completed with a barge. But tight sheets would have been installed on both sides of the trench and the pipe laid in between the two and then covered. That sheeting would have been removed. This case, with how long it was and due to the significant navigational activity of the boats there, we would have been required to have done it in at least thirds sections across the river to maintain that access, and also probably do it during spring, early spring or late fall to minimize impact to boats. Another concern with this option was mussels. There were some evidence of historical evidence of endangered mussel species at this location. And in order to get through the permitting process, those would have had to have been identified with surveys. And if they were present, would have had to deal with it accordingly from then on. The other option that we looked at was horizontal directional drilling. Horizontal directionally drilling, if you're not familiar, the picture on the right is how you would typically see it. Just driving down the road, you often see these on the side of the road, small setups like that, installing communication lines usually. These rigs are designed to insert a rod, a small diameter steel rod into the ground, and they transverse horizontally once they're at depth. And then you come out on the other end of your crossing or drill. Once it's out, then you would use what's called a reamer head, and you pull that back towards the rig, and the reamer head will enlarge the hole. And once you get the hole to the size you need, then you can pull the pipe in from your far side towards the rig. During that whole process, bentonite mud, slurry mud is injected to keep the hole open. This technology is, relatively new. I believe it started being introduced in the late 70s, but it's become much more prominent in modern days now. And they're getting pretty risky on these things, doing some very long, big diameter bores now. But it is also very common in river crossings. Ultimately, we decided this was the best solution for this location, and that was what was pursued. So in looking at a horizontal directional drill, we looked at 3 alignments to try to figure out what's the best way to do this. And when we look at these alignments, we looked at room for available room for equipment on both the entry and the exit sides. And then we looked for room for pipe staging. We have a significantly long pipe that we have to pull in, and ideally you want it in as few pieces as possible. So for a 3,900 foot crossing, the ideal world, we would have close to 3,900 feet of pipe strung out on the ground. And then we look at soils on the crossing and the river bottom profile that assists us in determining depth. Here we looked at 3 primary locations. See one there along the US 31. That one resulted in 3 crossings, but they were short crossings. That route was ultimately discarded due to the additional land-based pipe that would have had to been required to extend it to the wastewater treatment plant, as well as access along MDOT's right-of-way on US 31 would have made it very difficult to complete that bore there. So then we focused on 2 other locations. The one in green there comes from the wastewater treatment plant almost straight north. And on the north side in Spring Lake, that was a village park. And it was a great site with access, a great area for staging equipment. However, that site also is known for being a historical dump site, and drilling through that type of material was not ideal. So again, that option was discarded. So ultimately we settled on the location, which is Cutler Street. It's a road end site, and it had access. So this is a aerial view of the Cutler and Road Street and photo of it. Here we had approximately 310 feet of straight road end right of way that we could work with. It was about 83 feet wide. Really, there was only one house that we had to contend with here that was located at the end of the road. So access to local businesses and residents would be pretty easily maintained at this site. And there was enough room for storing of equipment. The equipment that we needed at this site on the entry side is pretty equipment heavy. So we have the drill rig itself, which is typically the size of a semi-trailer in this location. And the rod itself would then extend another 10 to 20 feet in front of that. So we needed a straight spot of around 60 feet to fit the rig. Additional support equipment consisting of semi-trailers full of rods would have to be sited next to it. At least one excavator needed to be located there. Steering and controls, guidance, cabin would be located there. And then our mud recycling system would have to be located there, as well as generators. And since we were doing this during cold weather, they also needed heaters located on site. So there's a lot of equipment that had to been sited, but we felt this site was adequate for it. So the next thing we looked at here on the entry side is existing utilities. What's there? Can we fit this even in the ground? And there is an existing sanitary sewer there, a small diameter water main, an old gas main, and some storm sewer. The sanitary sewer we would cross, however, we were going to be probably 15 to 20 feet deeper than it. So that was not an issue. The same for the water service. The gas main did have to get relocated. So prior to our work, the gas main was relocated to a spot closer to the edge of the right of way. And other than that, I mean, the site was, for how small it was, there was not much in the way. So we felt this was a doable situation on that location. So then we had to look at the exit side. On the exit side, we were using North Beechtree Street. This is another dead-end road with a cul-de-sac, but it was very close to the wastewater treatment plant, which is located on the south side of that picture. And we were able to come in on an angle and come up in the middle of that cul-de-sac. The other thing we had to look at for this site was pipe staging. And we'll talk about that in a minute. And then we also looked at the exit side utility issues. There's a lot of utilities at the exit side. The biggest issue though we had on that site was the existing force main came through there, and with the proximity of where our drill was going to be coming up, we were very concerned that we could accidentally strike it or cause problems. So we actually had the existing force main relocated out of the cul-de-sac and into the new force main prior to the drilling. So that was one item that we did have to do prior to the actual crossing. And then pipe staging. So on the exit side, pipe staging is critical. Like I had mentioned before, we needed about 3,900 feet of room. Now at this site, we determined 3,900 feet was likely not possible. We did allow the contractor, if they desired, to bend the pipe through the wastewater treatment plant, and they could have actually gone to the extent of floating it in the river on the other side of the wastewater plant. However, that was deemed pretty complicated and they didn't want to do that. So they chose to do it in smaller sections. But this site had enough room to do what we needed to do. The fusing of the pipe was completed, everything that was north of Fulton Avenue. And there's plenty of room for staging. And again, really very little business impact at this site. So once we knew that we could fit everything where we needed to go and we had our alignment, we could then do a soils review. On this length of a crossing with over 3,000 feet in the water, we needed to get soil borings in the water because ideally we wanted them every 500 to 750 feet along the path. And we looked to go about 20 feet below the design path. Now that's a little complicated to do and we don't really know our depth. And the soils here were, I classified it as snot. I know that's not really the technical term, but it was clay on both ends, which was good. But in the middle, it was, like I said, just very organic-y, silty, snotty material that had really no benefits of that we wanted for the crossing. You could not really steer through it, but we felt the drill was adequate. We could complete the drill primarily because the clays on both sides made it so we could steer down to depth. And then once we got to the bad material, we'd be flat going across the river. So we felt like it was possible. The one thing we did know going ahead was due to that condition of the soil in the middle, the borehole would likely not stay open during the crossing. And usually you want that borehole open. By open, it means the native soils are no longer in the hole and it was replaced with a bentonite slurry mix, which makes it so the pipe can make it through. In this case, we were really just kind of conditioning the existing material through there and mixing it with the bentonite slurry mix and hoping essentially that it would all stay liquid enough to continue moving. So once we had those soil borings completed, we also did a bathymetric survey of the river. The bathymetric survey here was not too exciting. It's pretty flat or pretty shallow in this wide area of the river. I believe it was 14 feet deep was the deepest location in one of the channels. And we laid out our bore profile based on a minimum depth of 60 feet below the lake bottom or the river bottom and the pipe. And this was based on our hydrofracture analysis, which identified the strength and the capabilities of the soil to resist the pressures of our drill. So we had to make sure we were deep enough to account for that. That was the minimum though. However, we actually designed it to go deeper than that. And the ultimate bore path was about 110 feet below the surface is where the pipe was located. On our plans, this is basically what the plans looked like. We showed the entry angle and then a radius of the pipe curvature and the bottom invert of the pipe. Now, everything we did was kind of within a tolerance. So we said, this is our design path. You are allowed to select your own path. However, you have to stay within certain tolerances that we set up. And then on the exit side, we had a shallower angle exiting of 12 degrees. And basically the same information that we provided previously. So the next question was, what kind of pipe do we choose? There's 3 primary pipes that are utilized in this type of work. The 3 pipes are steel, HDPE, and infusible PVC. Steel is really more in the energy sector. However, it is very common to be used in these long drills. Because we're dealing with sanitary sewer, we did not pursue that option here. So we looked primarily at HDPE and fusible PVC. HDPE being the more common material used, especially around here and in the municipal world. So most people are very familiar with that. PVC was a little more unknown. It is used commonly, but not nearly as commonly as HDPE. So when we looked at those 2 pipes, the biggest thing that between them is HDPE does not have as high of a pull force. It can't handle as high of pull forces, which requires then that the pipe thickness become thicker. Whereas PVC, you can get a higher safe pull force at thinner wall size. It's just a stronger pipe. And when looking at that, due to the forces that we were seeing, you would get a greater weight in your HDPE due to the bigger thickness, which would also require a larger diameter pipe because we needed to meet a certain hydraulic capacity of the pipeline. And that kicked the forces of the pull up as well. So as you can see here, a fusible PVC pipe, we were theoretically calculating 113,000 pounds of force required to make the crossing, whereas an HDPE to meet the same requirements was 194,000 pounds of force. So it's a significant amount more force. The weight was twice as much, and that all kind of went into the cost. But the biggest thing we were looking at is how big is that hole that we have to create to get that pipe through the crossing. Knowing that we did not have good soils to deal with, we wanted to minimize that hole and minimize the amount of time we were going to be working to try to get that hole to stay there. So to us, the outside diameter was critical. That is ultimately what led us to the fusible PVC for this pipe. The other differences between them, fusible PVC it's kind of brittle. If you drop it, it will likely crack. If you run over it, it will shatter. Whereas HDPE will not crack as quickly. It's a lot more durable. It'll take a hit and it'll take a scratch. However, fusible PVC is also very strong. It acts a little different. It's more brittle, basically. The other benefit, though, it has a lower expansion contraction rate, and HDPE is a very high expansion contraction rate, which would mean in the long-term application here, the HDPE could either one shrink or expand. In our case, it would likely shrink, which would have required significant anchoring on the land locations. So we ultimately selected the fusible PVC for this application. And after that, then went out for bids, and Gabe's Contracting out of Sheboygan, Wisconsin was selected as the low bidder. They started setting up, it was in February of 2019. This is them setting up the site. As you can see, we're very close to a house that was less than 5 feet away from that building. And we've put up sound attenuating fence around the site for security purposes, and also just to try to knock the sound down since we were in a residential neighborhood. The equipment is not quiet and it's running most of the day. There they built a nice pad out of timbers and had to clear some brush. Ultimately, that was the location of the drill. This is what the site looked at once it was set up. They had not started drilling at this time. Again, the drill can be seen on that left photo on the left side. In the background, various support equipment is there, generators and heaters. And then in the big blue tarped area, that is actually covering their mud mixing machine and recycling machine. And again, you can see how tight this site was with the cones backing up right up to the driveway of the one house that was located on this street. Here's an aerial view of the site during drill operations. As you can see, you have the drill, which is the big thing looking like a truck, semi-trailer on the back with a rod extending down into the ground. There's the hole around that's filled with mud. That's the drill mud. And then next to the rig is just a support semi-trailer with additional rod pieces on it and an excavator there that would help load it. Then you see the mud equipment down at the bottom of the picture with pumps and pipes that connect that pumps the mud out of that hole, recycles it, then brings it back to the drill rig, and it's injected down the drill stem to the bottom of the hole. And then the little blue shed in the middle of the site there, that is the steering and guidance shed, which is where everything was done and tracking was all completed through there. Another angle of this, you can see they utilize storage around the south side of the site, around the building. Again, you can see how tight we are to the buildings. The interesting thing too on this site, you see the proximity of the Grand River to us. This was back in 2019 in the spring or early spring, late winter. That year is when we started having the really high Lake Michigan levels and the Grand River levels came up. And the water level actually rose to the point where almost up to that house's driveway in that picture was underwater within probably a month after we left the site. So the groundwater kept coming up, and to the point where the road that they were working on started just totally disintegrating and heaving during the construction. Again, another aerial view of just the various equipment here. And then this is the exit side. This is actually during pullback operations. On the exit side, you again have, on these longer drills, they'll have another mud system on that side as well. And this is because the mud's going to be coming out either end. So it can come out that far side when the drill stem tip is near the far side, and then you'd have mud everywhere. So you have to pump that out. So they have a pump there and they're recycling and cleaning it. However, at this end, they're actually loading it onto a truck, and then they drive it around to the other side and then refill the drill rig with that, so that don't just accumulate mud on this side. Just more close-ups of the equipment. Again, you can see the ice buildup all around the mud. It was cold throughout this project. And this is just a close-up of what the drill rod or the drill rig itself looks like. This is a semi-trailer mounted rig setup. They can tip it up to various angles, and it's pretty much all automated. There's a guy that'll go out there, slap some grease on the threads, and then the machine does all the threading. And it's actually quite slick process to watch him do. And then they just push it on down. Here's a picture of the tip. This is their mud motor tip on the end of the rig. This would inject, the drill mud would come out of that tip, and that mud is acting as two things. One is, or three things, it's keeping the hole open, it's lubricating the whole process, and it's circulating constantly. So it gets pumped down that drill rod, enters the hole, and then comes back out of the hole through the ground, follows that bore path. And with that, it takes the washings, the tailings, the soil that's coming out of it, and then that is pumped out. So that drill mud it's critical, and you want to make sure it's always recycling throughout the process. Because if it's not recycling and you're pumping it in, it's going somewhere, which means you're losing it in the environment. The other thing, you can't really, doesn't look very fancy, but right on the other side of this drill stem is actually what's called a gyroscopic steer head. And for this project, they utilized gyroscopic steering, which meant there was no ground wires or anything up above. It was all handled from that at the tip of the drill. That data was then coming back up a wire up the drill rod to the rig, and from that they could steer it and know exactly where they are the whole time. Throughout the process, they would provide daily reports, which included how far out the stem was, how far right or left the alignment, the elevation, the inclination angle of the stem at the tip, the azimuth, and we could also then determine the stationing, pressure at the stem down there, the annular pressure, which was critical when monitoring whether or not you would have a fracture out into the environment, and what joint they were at. This was then provided in a CAD format too, so you could actually build a profile as they progressed every day. And the accuracy with that gyroscopic was incredible. They were within tenths of the proposed alignment throughout. The pilot hole itself was completed in 7 days. That was just to get the pipe across. This is a picture, and what's kind of cool is you see the stakes in the background. Those are alignment stakes. They came out within 5 feet of our here stake, which isn't in the picture anymore, and within a foot of our proposed alignment from 4,000 feet away. But they weren't complete yet. So we ended up with 2 problems on this project. The first one is to hit an inactive gas line. And I had mentioned previously there was an old gas line that had to be relocated. Well, it was relocated, but the old one was left in a hole. And when they started trying to do reaming, they tried to do forward reaming, which was they actually pushed the reamer head instead of pulled it. And when they did that, they hit the gas main and wound it right around their drill stem. That's a 2-inch steel pipe, and it was just coiled right up. So that caused some issues, and then they had to cut that off. And then the bigger issue, the hole was, we'll call it tight, and they struggled pulling the whole drill stem back. They got it out there, but then they couldn't get it to come back towards them. And what they tried first was a weeping sub, which is a picture to the right. And that is just, it's a short piece of stem basically that has some holes in it. And the holes would inject more mud trying to lubricate everything. And then it did not really work. They were only able to get it to come back a couple 100 feet. They tried an air hammer, which is the picture on the left, which is just a big hammer that they set up on the end of it, trying to just vibrate it and shock it into movement. Again, that did not work. And what ultimately happened is the drill stem itself, which this drill stem was a 7-inch steel pipe, snapped at about 40 foot of depth, which was about at the edge of the river on the entry side. At that depth, it was not salvageable. So at that point, they had to start over again. So they shipped out more rod from Sheboygan. They got it out here and repiloted it. It took them another 7 days to repilot it. They just offset it and go slightly deeper than the previous one. And that went very smoothly, and they made it. That one did not have any issues with being tight, so they were able to start back reaming operations immediately. And that was completed in 7 24-hour days. They did it in 2 shifts. And the picture on the top, that's actually what the reamer looks like. It's got a lot of teeth on it. It's aggressive and it turns. And then they are injecting a lot of mud at that time to try to get all those tailings to come back. Once that back reaming was completed, they did a swab pass. Swab pass was done with, it looks like a 50-gallon drum essentially, or a pig kind of, and they just pull that through real quick. And that's just to make sure there's no big obstructions in the way. They're not really trying to make the hole bigger, just make sure it's clean. And then the next step was pullback. Pullback operations were completed in a single day, 14 hours nonstop. Because of the site limitations on size and lengths of the pipe they could handle, they chose to do it with 5 mid fuses, which meant they had 7 sections of pipe fused up, and they would pull one section in, and once they got that all the way in, they'd quick fuse another section to it, and they would pull that in. And each section, I believe, was around 700 foot long, except for the first and last were short. And it went very slick. They had multiple excavators on site, lifting the pipe onto the rollers. They're all supported on rollers. As the pipe was pulled, the next one was pulled up behind it, and it only resulted in about a 45-minute stop for the actual fuse throughout the process. And then the other thing we used here was a buoyancy control, which we'll talk about in a minute. So this is just a picture of what the site looked at entry. So these are the last 2 pieces of equipment before it actually went into the hole. You can see there on the right, the fusing equipment set up. So the pipe was basically just pulled right through the fusing equipment throughout the process and then stopped when necessary. I believe this picture is actually taken during a mid-fuse being completed. Here you can see what it looked like. We had 4 pipes strung out right there in this picture. You can see the one that's on the rollers that's being pulled at that time. Then you got 3 to the left. Those are all being staged there and would then get pulled onto the rollers once that line was done. Aerial view of what this looks like. So the picture on the left, you can see the one excavator is actually holding up the pipe. That one's being pulled at that time, so it's just keeping it from dragging on the ground. The excavator directly behind it is the one that's picking the next string up and setting it on the rollers as they go. And then we mentioned buoyancy control. So when you drill these pipes, you have a hole that's about 1.5 times the diameter of the actual pipe. And the pipe wants to naturally float to the top, which causes greater friction and forces on it. So on these long crossings, you want to try to reduce your force. And one way to do that is to buoyancy control it, which is you try to sink the pipe and try to target the middle of the hole if possible. So the way to do that is by adding water. So water in this case was added, and this photo shows they had a 4-inch HDPE line that was extended down the pipeline, which they then used a hydrant to add water to. This was added at about halfway through the drill, and it reduced the pullback at that time from 104,000 pounds, which is about midway through, which forces continue to go up as you go. And it dropped it down to 80,000 pounds. And it stayed pretty consistent, just around 80 to 90 the rest of the project. So after 14 hours, they were successful. And as the whole job was, it ended in lousy weather with it sleeting and being frigid cold, but they made it. And it was a lot of relief, and we no longer were not sleeping at night once it was complete. So it was nice. And then final items, they flushed the pipe here. You can pig these lines. We did not pig this line. We were too nervous about getting a pig stuck in the middle of the pipe, and figured it didn't matter too much in this case. Pressure testing was just standard hydrostatic pressure testing. And then the connection was made once the land portions were complete. And using fusible PVC, we were able to just use standard ductile iron fittings. In this case, this is C900 pipe. And here, this is not a standard mega lug. This is a special mega lug just for PVC, and it's a full rating of this size pipe, so it's a double setup. But it was a very easy connection to make. So with that kind of ends my presentation. It was a fun project to do, and it was successful. And to this day, the pipe is still working well, so that's good. So if you have any questions, I'll take them.
Yeah, thanks, Matt. Yeah, so we'll just open it up. If you have a question, just kind of unmute yourself and ask Matt.
Eric had dropped something in the chat, and maybe this is more of a comment, Matt, but talking about when you were discussing pipe selection and how you selected what pipe you were actually going to use. Eric's comment was just that he thinks that you guys rejected steel pipe just because of the corrosion due to what you were going to have to convey, or the sewage in that pipe.
Yeah, primarily that is why. I mean, we also considered, would we just use it as a casing pipe and then string a new pipe inside it? But that seemed kind of redundant for our application. But yeah, steel pipe, we would have had to lined it, and just, it's not common either in this application for the authority to be trying to maintain that pipeline. Would have been a little outside their wheelhouse, so.
Yeah. Do you know what the lifetime of this fusible PVC looks like?
It's comparable to an HDPE. We're expecting 50 to 75 years of life out of it.
Hopefully at that point, I would think you could just insert a new pipe inside of it and break it, right? That'd be a way to approach or do you
That
have
would
to
be
bore
the
it again?
goal. If it's the technology for pipe bursting has not arrived yet, that can handle that type of a length. We actually looked at that for the other Forcemain, but that one had some bends in it, and nobody said they could handle that kind of a length and complicated bursting. So yeah, hopefully at that time, that type of technology exists and that could be pursued.
Hey, Matt, this is Joel Morgan. What do you think made the first pilot hole too tight to pull the pipes back? And then if offsetting just a few feet, why did the second one work but not the first?
We're not 100% sure why this occurred. The leading theory that we have and the contractor has on this is due to like I had mentioned before, there was hard, stiff clays on both ends of the bore, which was critical for steering because you can't steer through the really muddy stuff. But when they started coming up, they they think what happened is they were pushing too hard and hit that clay wall coming out of the soft stuff. When they hit that clay, put a straw, like a plastic straw, push it up against a wall and see what happens to that straw. It buckles. And what they think happened is that long drill stem hit that wall and sort of buckled. And they actually did find a rod in the process of pullback that was kind of buckled, which then pushed it out of the conditioned path. And what that resulted in is they think the whole thing kind of buckled in multiple spots, creating a corkscrew effect into the soil, which basically made a giant soil anchor, like you would use just to anchor down your playground set. And that's the running theory on what happened. The re-drill, they kind of had that theory in their head that might be what occurred. And so they took it a little less aggressively. Instead of hitting it as hard as they could when they hit that clay, they went a little slower. They also did change their angle a little bit. And when they started their radius of curvature to try to hit it more square and not on an angle. And it was successful. I don't know how much that was what did it or not. We'll never know, to be honest with you, but it was effective there. And that's what was important.
Matt, I have a question about the state permitting. How much permitting was involved with this? Was it less extensive maybe as doing the open method you talked about? Can you maybe talk about what your work was with Eagle or the DNR, DEQ through this process?
Permitting for this project really wasn't too bad because we picked the horizontal directional drill method in the significant depths that we were going. We weren't trying to go shallow. We went deep on this. Actually, Eagle does not require a permit because we weren't crossing wetlands. We were crossing open water. Because we were over 15 foot of cover, we got around that. Now, if we had happened to have a hydrofracture and mud got into the river, that would have then been an issue and we would have gotten permits and do cleanup. Thankfully, it did not occur here. We did need to get a permit from the Corps of Engineers for this because this is considered a Section 10 waterway. Really, that process again was pretty straightforward. Not overly, it's just their standard application. Again, the depths we were going and where our entry and exits were located outside the ordinary high water mark, outside of floodways and all that kind of floodplains, made it so that we didn't need those permits. And it went rather smoothly, actually.
All right. Any other questions for Matt? Kara, do you have anything else?
I don't think so. I was wondering when you're talking about the Army Corps permits, I think that has to do with like what kind, how navigable that waterway is right there. And they do some dredging in that area, don't they, regularly?
The Corps does. The primary channel for the Corps of Engineers at that location ends at the US 31 bridge. So they're not doing massive dredging anymore here. I think at the bridge and towards the lake is maintained at around 25 feet depth, I believe. In this area, it's just more personal watercraft and small boats. Now, like I said, we were 110 feet below the surface, which resulted in about 80 foot of cover between the lake or river bottom and our pipe. So dredging, the Corps basically looked at it and said, you're not going to hit it. So as long as nobody's driving 80 foot deep piling out there, there should never be anybody touching that main.
All right. Well, thank you again, Matt. Appreciate it. That was a pretty neat project and appreciate you sharing that with us.
Thank you for having me. It's nice.